Thank you very much, and I'm very happy to present this work to you. So I'm going to talk about scalable on-demand mobility services, and this is work with a large number of people. So I will introduce those people as I go along. The two main projects that I will talk about. So I'm going to start by talking about challenges and opportunities in mobility, and then I'll talk about two projects that we have been pursuing in the last 3 to 5 years, even more. One is on-demand multimodal public transit, and the other one is community-based trip sharing. I'm going to start with the challenges in mobility, such that, that gives you the context of why we are doing this work. So in the United States, we have massive congestion, and I'm assuming that this is in many parts of the world as well. It's going to reach about $200 billion in 2030, and it affects both large and small cities. This is pictures of Atlanta on the right that you can see. I can tell you that I'm driving in this kind of traffic every morning, and it's particularly painful, and it's going to get worse and worse as more people move inside the cities. If you look also at greenhouse gas emission, once again, this is increasing tremendously. At this point, transportation is about 33% of greenhouse gas emission. And out of these 33%, 60% is about light vehicles, light trucks. You have cities like Paris at this point, which are essentially considering using free public transit for reducing pollution. That gives you a sense of the magnitude of the problem. This is another fundamental challenge faced by a lot of the transportation system, and it's called the ubiquitous first and last mile problem. What you see on this graph is the market share of transit system as you make people walk to the transit system more and more. And what you can see here, if you make people walk about a quarter of a mile, 400 meters, what you see is that most of these transit systems are losing about 80% or 90% of their ridership, except these cities in Canada, Calgary, which for some reason people are willing to walk a lot more than other people. So if you want to be successful as a transportation system, you have to be in this range. You have essentially to make people walk very, very, to make people walk only about 50 yards or not more than that. Mobility is also important for a variety of reasons. So in a city like the United States, if you have a car, you're much better off than if you don't have one. And it's actually a stronger predictor of social mobility than the quality of your neighborhood, the crime in the neighborhood, the quality of the schools. It's very interesting. Healthcare, it's once again, and this is data in the United States, but it's also valid in many other countries. You have a lot of people with health insurance, but they cannot get to the care. They don't have the mobility options to get there. And this is what I found very interesting as well. In many countries, people don't live within 1 mile of a supermarket, and therefore, if they have to shop, they don't have many options, and they typically go to convenience stores where they don't have the quality of food that would be good for their health. So once again, mobility is preventing them from a more interesting and more healthy life. This is actually a very interesting anecdote here. So this is a city in the US, Detroit, and there was a supermarket chain, a super value grocery store, and they were basically offering Uber rides for everybody who would spend more than $50 at the store. I don't know if they still do it, but they were doing it in 2015. So these are some of the bad news and some of the difficulties and the challenges that we are facing. What I want to talk about now is a little bit what the technology enablers are. So what would enable us to actually change this? And the first one is going to maybe be a surprise, but this is connectivity. This is the ability to actually communicate between people and infrastructure and transportation system. The fact that we can communicate in real time with anybody, for me, is the main enabler. That will allow you to change transportation in very fundamental way, and it's already happening, obviously. The other thing that may change at some point is automated vehicle, autonomous vehicle. It's difficult to predict when they will be available, under what shape, on what form, but in one form or another, they will appear in some of the transportation system. And they will make a significant difference, and I will tell you why later on. And it's not only safety, it's also other issues, as you will see. And then finally, and this is where a lot of my group is spending time, I think what has been happening in the last 10 to 15 years has been a tremendous progress in analytics. And this is a slide that I borrowed from one of my friends at IBM. And it basically tells you the various levels of analytics. And most of what we do in transportation is covering all these levels. So we start by what is called descriptive analytics, understanding a system, getting the data, analyzing the data, understanding what are the bottlenecks inside a system. And then you move to predictive analytics, which is typically trying to predict what could happen if you do something. And then afterwards, the most challenging part very often is prescriptive analytics. That's when you design systems, when you design different mechanism, pricing schemes, and so on, and obviously the operations and the pricing schemes to operate the system at scale. So this is where my group is spending a lot of time, and you'll see that in the rest of the talk. So I want to talk to two projects. One is called On-Demand Multimodal Public Transit, and I'll spend most of the talk talking about this, and then I will move to community-based trip sharing. And once again, what you will see is that they mostly use these two aspects that I talked about, connectivity and then analytics, sophisticated analytics. So the first one is joint work with a lot of people. It started in Australia with Phil Kilby and Artur Mateo. And then we had a big ORITMO team, which is still in place, using various people. We worked with people in Australia and also people in Michigan, and I will show you some of these results in a moment. So the key idea there is that we are designing a completely new transit system, and it addresses many of the limitations that I've shown you before. So the first one is that we want this system to be on demand. We want to be able to address the first and the last mile problem. So which basically means that we're going to pick people up and drop them off very close to where they live or very close to where they want to go. And so they don't have to walk very far, but they are going to be, they are going to be serviced on demand and very fast and very close to where they want to be picked up. And then the system is going to be multimodal. And the reason we want it to be multimodal is that we want to address congestion. If we only do a purely on-demand system, I will show you that this would create massive congestion in various cities. Excuse me. So the system is going to be organized as a set of different vehicles, buses, rail, shuttle cars, bicycle or scooters, which are very trendy right now. But it's going to be a various modes, but we are going to basically assemble together in one system. So it's going to be on demand, but at the same time, it's going to be multimodal. We also want the system to be as much as electrified as possible, so that we reduce the greenhouse gas emission if you basically operate the system together with renewable energy. And then we also want the system to be a public transit system. So in the sense, what we want is that the cost of this system is actually a fraction of the cost of Uber and Lyft, for instance, such that you can actually use the system for your daily commute. And so I'll go over these aspects in a lot more detail in the next couple of slides, but this gives you the idea of what are the objectives at a high level of the system. So this is a little bit, at a high level what the system does. So you have these shuttles that are, so this is only 2 levels, probably most systems for real cities. For large cities, we'll have 3 levels. But what you see here is a shuttle, which is going to pick up people and bring them either to their destinations, or if they have to go through a highly congested corridors, we'll go to a hub, where people will basically travel to a high-capacity bus or high-capacity rail, and then they go to another hub when another vehicle is going to wait for them and bring them to their destination. So it's multimodal because we have different types of vehicles. It's on demand because these shuttles are picking up people at their place or very close to their place and bringing them either to their destination or to a hub. And if they go to a hub, another shuttle is going to take them up afterwards to bring them to their destination. So the key point here is that you have to understand that this is one system. So you book one ticket online, it's completely integrated and optimized globally. The pricing is the same as a transit system. So it would be, in the United States, it would be about $3 to $4. And the transfer are completely synchronized. It's not like you are, at a place and you don't know what to do. The app is going to tell you, hey, this is the bus that you have to board, or this is the shuttle that is waiting for you. And then the buses or rail are only on the high density corridors. They don't serve the very, sparsely populated region. So I want to illustrate this on a couple of case studies, 2 of them. The first one is the city of Canberra in Australia. Canberra is the capital city of Australia. It's a city that was built about a century ago. And it's built by this American architect, Walter Griffin, as what is called a green city. It's essentially a set of self-contained communities separated by green space. So it's very spacious, very nice to live, very green. But the problem is that because it's so spacious, it's very difficult to operate an effective public transit system. So for instance, if you look at the off-peak bus service, the routes are very long. The frequency is very high, is very low, sorry, about an hour. So the buses are running almost empty, and because of that, they are very expensive, and therefore nobody is happy. Customers are not happy, and obviously the city is not happy. So what we did was trying to look at a system which is on demand and multimodal like that to address this issue. So what you see here is a demo video, a 3D video showing you what this system is. So blue here are the buses. The taller they are, the more people there are in the buses. Red are the basic stop. You see a bus hub there, another hub over there. And the green are the little shuttles that are picking them up. And once again, the taller they are, the more people are in the shuttle. And they can host about 4 people in this particular case. So you see, for instance, my cursor here is following a bus. It's going to basically arrive at the hub where people have been conglomerating, is picking up all these people, and the bus moves to the next region. And what you can see here is, look at the shuttles, they are bringing more people to the particular hub again until the bus comes and so on. So this is how the system is organized. And the other things that I wanted to mention here is that you can see that there is a huge amount of bus stops there. And the bus stops are widely distributed across the space, and people don't have to walk very much. So it's essentially an on-demand system where people don't have to walk very much, but they are not really picked up in front of their house, but very, very close. So what is interesting is to see the saving and the convenience which is bring up by this system. So what you see here is the system that we design and simulate. This is the existing system. And one of the big things that you see there is for various days of the week, you basically decrease the cost by a factor of 2. And you decrease also the time or the transit time by a factor of 2. So it's a significant benefit here, both in cost and also in time. These are some graphs that are also illustrating this system at various aspects of this system. So this is the total cost that you see there. And so the x-axis here is the convenience. The more you move to the right, the more you increase convenience, so decrease transit time. This is the cost of deploying the bus. Obviously, as you increase convenience, you reduce the number of buses, increase the number of shuttles. This is the price of the shuttles here, which is increasing with the convenience. And this is what I find the most interesting. Essentially, as soon as you start, putting some more convenience, adding some of the shuttles, you dramatically reduce the transit time, and you don't increase the price too much. And that's how we can actually have a system which is at the same time less costly and actually decrease the transit time. Obviously, in practice, you can play around these 2 parameters such that you match best the configuration of a particular city. So this was essentially a city which was very widely geographically dispersed, and where the routes were very long. And so what I'm going to talk about now is a completely different case study, which is kind of completely the opposite. It's a very small area. This is essentially a college town, and with a very high ridership. And I'm going to show you that exactly the same design works in this context as well. So this is Ann Arbor, which is the city hosting the University of Michigan, and it has 2 transit systems, one by the city and one with the university itself. And this is a very densely populated area, a very small and densely populated area, mostly because there are a lot of students. And so you have about 50,000 commuting trips a day in this 4x4 square mile area. And so the 2 systems are very well operated. They are operated with about 75% utilization, 75% capacity, sorry, which is well above national average here in the United States. And they're also a very interesting congestion issue. A lot of students are trying to board these buses, and at various times of the day they cannot actually get into the bus. Although these students are very good, believe me, in packing a bus. So what I'm going to show you now is a 3D video showing you the life of this transit system. One day in the life of the transit system, but this is like 3,000 times the speed. So I don't expect you to actually notice anything except the big trends. And once again, the buses are blue and red are people waiting. And what you can see here is essentially that they are very heavily corridors. So this is like in the morning now, you see this corridor is very heavily used. This is another corridor which is heavily used because the university is spread across essentially 3 different campuses. So a lot of people waiting as well, as you can see. So this is to tell you that this system is not easy to optimize in a sense. So what we decided to do is we wanted to keep the buses because they are heavily congested corridors, but we shortened the routes in the simulation such that they essentially only cover the congested corridors, nothing more, but we increase the frequency as well. And then the second thing that we did was introducing the shuttle again, and this is a larger shuttle than the one that we had for Canberra. They can host about 8 people. And so this is one last winter, not this winter, the previous winter. And what I'm going to show you is before and after. So this is the system before the existing system, and then the system that we were proposing for addressing this first and last mile and addressing congestion as well. So this is the existing system in the morning, 8 a.m. And what you can see, once again, the buses are blue. You can see them heavily used on these particular corridors, also for the South Campus here. But look at the Northeast here. Look at these buses. They are almost empty. They have about 5 or 6 people, sometimes 1 or 2. They're basically running empty in that particular area. And so the first time I saw this, I said, why are they running buses inside this campus? But obviously, these buses are very heavily used inside a heavy corridor. This is the same existing bus system, but in the evening, where the frequency on the buses is lower, the buses are coming, twice as slow. And what you can see here is, again, is a lot of people now are waiting here. A lot of the students are waiting. They're still moving along about the campus very heavily at that particular time of the day, but the frequency is lower, so they wait much longer. Although the buses are more heavily used because of that. So what I'm going to show you now is the new system, exactly the same time, exactly the same data, and this is 7:30 again. And now you see these green shuttles that are basically servicing the first and the last mile, the first and the last mile. And what you can see now is that the people are not waiting anymore. They are served very, very quickly. The only red bars that you see are the bus stops, and they are picked up very quickly because the frequency of the bus is about 2 minutes. So it goes very, very fast. So once again, what I'm showing you here is the system where the buses are servicing these very heavy corridors, but then you have these shuttles which are basically bringing people to these very heavy corridors, to the hubs, and avoiding congestion that way. At the same time, servicing the first and the last mile very effectively. I'm going to zoom on this thing because we do automatic ride sharing on the shuttles. So you see these shuttles there. Once again, the taller they are, the more people they are. You see this shuttle here that I'm following my cursor. That's probably about 4 or 5 people. Some of them are only 1 person. Some of them, this is probably 6 people there. So once again, so this is probably 8 people. Once again, automatically the shuttle would will automate ride sharing, provided that we don't exceed 25% of the shortest path for any of the passengers inside the shuttle. So once again, this is a system combining 2 modes, but also doing automatic ride sharing on the shuttles. So let me show you some of the results here. One of the big things that we did was essentially decreasing the transit time such that it's an average of 14 minutes. So most of the time, if you take your car and doing transit over there, you would take about 12 minutes. So we are very close to the transit system, to the performance on a car on this particular campus. Many of the trips are actually 1 leg, 2 legs, so which is a bus or a shuttle, and then 2 legs would be a shuttle followed by a bus, or a bus followed by a shuttle. That's because this system is very, very dense. This is an interesting study here because now the cost is completely different. So what I'm showing you is the capital expenditure of the system, as well as the cost of the drivers and the fuel and the insurance is everything. Everything is included in there. And what you see is that essentially now most of the costs are the driver cost, either for the shuttles or the buses. We have basically reduced the capital expenditure tremendously. And so the day we basically have autonomous cars or autonomous buses, this cost is going to further reduce and we can improve a quality of service even better. No, we optimized this so that we fit in the budget of the transit system. So what we did was making sure that we improve quality as much as we can while not exceeding the budget of the transit agencies. So automated vehicle in this particular case would make a very big difference in terms of cost. So let me talk a little bit about the deployment that we did. So we had written these mobile apps for actually doing these kinds of mobile application. They are essentially, Uber and Lyft on steroids because it's multimodal. So I don't want to go into too much details, but I want to show you this particular concept here. We have this concept of virtual stops, and that's where people wait for the shuttle. So we don't pick them up at their homes. We want them to be ready, but these virtual stop can be put anywhere, and that's where people are basically picked up. And because of that, we can do ride sharing in a more effective way as well. So we spare some time, and at the same time, we can do automatic car sharing and optimize ride sharing. So this is an interesting data point that I wanted to show you. So the existing transit system would stop here at this road. So everything north of this particular road was not serviced by the transit system. And what you can see is that a lot of the rides are actually coming for this particular area. So this is the alightings for that particular area. So this is one big residence of students and staff. So there is really a first and a last mile problem here. And this is what the system is actually addressing in this particular case. This is interesting as well. This is not a residence. This is actually a supermarket as well as some restaurants and so on. And what is very interesting here is that a lot of people are using the transit system to do grocery shopping. So, which is one of the motivations that I told you before. This is interesting because this is a housing complex and there is a bus available to go there. But the students like the on-demand services so much that essentially there was a mode change there, which is very interesting as well. This is the waiting time of inside the deployment. It varied between 3 minutes and 5 minutes, depending on the number of shuttles that were deployed on that particular day. So which was kind of nice. So this was a very, very small waiting time. Very competitive with what Uber and Lyft would do. But this is a transit system, and the cost would break even around $3 to $4 again. Behind the scene, we do a lot of optimization and machine learning. This is at the high level what we are doing. So we start from the road data. We do a lot of analysis and machine learning for finding exactly what people are doing. It's mostly activity-based models, OD pairs over time, and things like this. Then we do the mobility system design, and we design the mobility services, and then we run them at real time. So here it's a lot of network design with very sophisticated optimization techniques. This is essentially online optimization, where we maximize ride sharing and we minimize waiting time. That's essentially what we do there. So there are a lot of very interesting optimization algorithms, machine learning algorithms to do this. So that's what we are doing behind the scene. So I want to take a little bit of a step back here and tell you and reposition the work that we just did. So one of the things that has happened in transportation in the last 10 years, I would say, is that we have reinvented taxi services. So Uber has really reinvented taxi services using ride sharing and ride sourcing. And this has been a very fundamental transformation. But this has been essentially, changing taxi services to make it, to the 21st century in a sense. And so what we are trying to do in this project is essentially taking public transit and doing the same transformation. That's essentially the project that we are trying to do. We try to do essentially bringing transit into the 21st century. And to give you a sense of why we need to do that, if you try to have Uber and Lyft operating the transit system of the University of Michigan, for instance, you would spend about 10 times of what I've shown you in terms of budget. You would need essentially to spend 10 times the budget. And this is the number of shuttles that you would have to use. You would create massive congestion on some of these corridors. So I think there is a big need to actually change transit to bring new technologies, but they have essentially to be multimodal to avoid this cost and also these congestion issues. This is not new. What I'm telling you is not new. It's well recognized that Uber and Lyft are increasing traffic in major cities. You see some examples here in New York City, where I think the current numbers is 3 to 4% increase in traffic because of Uber and Lyft. And one of the side effects of this is that it has put a lot of pressure on transit systems, and these new systems, they are so effective for various activities that they have taken some of the budget of the transit agencies. So it's dangerous in a sense. And so what I want to give you in 2 minutes is essentially what happened in history and how public transit and taxi have evolved in parallel, such that we don't make the mistakes of the past. And so it's very interesting because I did some research to actually find out who invented public transit. And it's actually a mathematician. So this was invented in the 17th century by Blaise Pascal. And so this is very interesting to see what they did. They had this carriage that operated in Paris for about 15 years before it stopped. It was resurrected in the 19th century. And it would run one of the main arteries in Paris between La Bastille and La Madeleine. And that was also very interesting because it was basically running every 15 minutes, and that's how it looked like. So, it's very interesting that there was public transit at that point as well. And one of the motivation there was accessibility. It was essentially showing you that you can now connect different neighborhoods in Paris, and these neighborhoods were not connected before. And so this bus line actually stopped for 2 reasons. One is the fare were increased, and then instead of moving as a public transit system, it moved to specific segments of the population. So I think we have to be very careful now and also avoid exactly the same mistake. Also, one of the things that I wanted to tell you is that over the course of history, public transit have been very quick of adopting new technology like railway and so on. And taxi services at the same time have followed exactly the same path. So they started in London and then in Paris, roughly the same time. And then they adopted technology as they went along as well, using these hummingbirds, for instance, in London, and similar vehicles in New York City. And obviously, at the end of the day, we got, taxi services like in New York City, and then Uber and Lyft. So what I'm basically telling you is what we have to do now is to make sure that this later stage in innovation, in technical innovation, goes to public transit as well, such that we can actually improve accessibility for everyone, not repeating the mistakes that have been done in the past, and also decrease congestion, decrease greenhouse gas emission, and addressing the commuting issue, not only the taxi services. So that's one of the things that I wanted to talk about. So I'm going to shift gear a little bit and then talk about another a community service that we have been exploring as well. And this is what we call community-based trip sharing. And this is work with a couple of my students as well, and also Sharon Budak, who is in the School of Information at the University of Michigan. And so I'm going to motivate this with the most boring 3D video that you ever seen in your life. So what you see there are the 15 most used parking lots at the University of Michigan. And so the parking lot, the taller they are, the more cars there are in the parking. And as you can see, up to 9 a.m., they're basically increasing, and then afterwards they don't move. So people are basically putting their cars there for about 8 to 9 hours, and these cars don't move. So you have to realize that a parking spot in one of these lots is about $40,000, and these cars are basically taking these parking lots for the whole day, except one, which is essentially the medical school where the shifts are inverted. So the person running this parking lot came to me because he had a lot of pressure on increasing the parking lot to see, can you actually address this issue? Can we actually decrease the people using this parking lot? And what I'm going to show you is one effort that we tried to do for doing exactly that. So what we did was basically viewing the region as a set of communities, and we tried to see, can we actually ride and car share as much as we can in that particular community. And so the goal obviously is to minimize the number of cars on the road, because if we minimize the number of cars on the road, we're going to minimize the number of cars in the parking lot. And so what we are given is that we know when people are leaving their home and arriving in the parking lot, and also when they are departing the parking lot and going back home. So we had all this information for everybody on using those parking lots. And the only assumption that we are making is that people are willing to move their departure time either on the way in or the way out by a very small intervals, like 5 to 10 minutes. such that we have some flexibility. And so we try to see if we can actually do something like this. And if you look at the literature, most of the carpooling services are not working very well because there is a lot of difficulty in matching people and schedule and location. So we wanted to do, what we wanted to see is that, okay, so we have sophisticated analytic capabilities here. We have all the data. Can we actually find a matching platform that would reduce the number of cars and be a successful carpooling operation? Can we do that? And so the first thing that we ask is, what are the successful properties of the platform? Once again, we read a lot of papers, and I'm going to show you a number of these principles that a platform like this has to satisfy to be successful. The first one is we want the rider to be close together from a spatial standpoint, and then they have to be also close temporally. Obviously, they have to have roughly the same schedule. So these two are non-negotiable. And then the third one is also not negotiable. We also want to make sure that if somebody is using the service to come to work, that person has the same, that person is guaranteed a ride back home. So essentially, this has to be satisfied. There is no other way. And then what people typically like is low coordination costs. So they would like to ride with the same people every morning, every evening. They also would like the same people every day of the week. They also, would like to know the people. They have to be in the same community. And they also would like to have clear commuter roles. So if somebody is driving every day. Something is a passenger, that person is a passenger every day. So what we try to do is build a model that had the first three property and try to see if we could add more of them to have to make the platform as successful as we can. So this is the data that we have. So these are all the people commuting to this parking lot. This is a very large region, about 50 by 50 miles. This is the timing of these people. X-axis is entry time, Y-axis is exit time. And you see that a lot of people are coming in the morning at, in normal hours between 7 and 10, and then leaving between, 3 to 5, 3 to 6. Except here, once again, what you see there is the hospital shift. This is the night shift for the doctors, the nurses, the staff as well, and the visits as well. And this is a very interesting picture. This is essentially the data when the commuting patterns when people are coming in the evening and when they are leaving in the evening. And what you can see here is that people are highly predictable. They mostly do the same thing every day. So they come at the same time, they leave at the same time, and so on. So we are extremely predictable in the way we are commuting to work. And so we said, okay, so we should be able to actually have a system which is, carpooling people very nicely. So we tried, as I told you, to have these various optimization models there that are satisfying this principle. So 1.3 is just the basic model, the first three principles that I showed you. And then afterwards, we try to add them more. And what I'm going to do is jump directly to the results because they're very interesting. And then I will explain how we get there. But what you can see here is, this bar here is essentially when you don't share, this is 100%. And then the next bars are essentially, implementing the 6 principles, 5, 4, and then 3. And what you can see here is that if you try to have the same people commuting every day, every morning together, essentially you only save 2% of the cars on the road. So you basically cannot really optimize that. And this is the primary reason why carpooling systems are not very successful. What you need is the ability to actually match people online every day, every morning, every evening. And if you do that, then you can save, in this particular case, about 45% of the cars. So you basically decrease the number of cars in the road by a factor of 2. This is inside the city. So this is a smaller region. And then what you can see here is that we basically reduce the cars by a factor of about 3. So about 2/3 of the cars have been eliminated. But once again, you see this very similar trend. It's when you have the full flexibility that you can optimize online that you essentially get these large savings. If you want the same people to commute every day in the same way, once again, you only save about 4% of the car in this particular case. So how do we do this? The first thing that we do is we basically do a large clustering algorithm. We do a k-median first, then we optimize the size of this cluster so that we minimize the travel time. And you get, so this is for the whole region, you get these various clusters, special region, which are essentially different communities. You can see the various, small cities, small villages over there. This is outside the city. I think I'm going to show you the inside the city there. You basically have the neighborhood and people are clustered by the neighborhood. So we have the spatial locality automatically. And then the only thing that we have to deal with is the temporal locality afterwards, and the right home and the guaranteed right back. This is what you see here. So that's the next step. That's the optimization model that is essentially ensuring that you have a right back. So we basically make sure we minimize the number of routes and the distance as well. We serve every customer on the way in, on the way out, and we make sure that we have the same drivers on the way in and on the way out, such that we guarantee a right back. So that's what we did. And obviously, we have to do a little bit more than this. We have to generate the routes, and generating the routes is a very complicated problem. What we have is a branch and price algorithm, which is basically using a constrained shortest path for generating some of these routes. It's a very sophisticated one because of the nature of the problem, but it can be done, and I will show you results that it can be done in almost real time as well. So let me skip this because these are too many details for this particular talk. So let me go back and talk about some of the reason why this problem is not so easy, and what we can actually save. So what this is showing you here is interesting. It's the impact of the vehicle capacity, and on this particular test cases, which has about 15,000 riders here. What we show is that the vehicles, they cannot be that big, because at some point when you reach the size of about 4, there is not much benefit anymore. Same thing for the road distances. You don't save anymore as the vehicle is 3 to more than 4. So essentially, this is a system that operates with small cars. This is the effect of this of increasing the vehicle capacity on the right, on the duration of the ride. And once again, you see that there are not much benefit in losing very large shuttle in this particular case. This is the impact of the cluster size, and what you can see here was what you expect. The larger the cluster, the more significant the saving in the number of cars. And obviously the optimization problems become more difficult, but we can solve n to 400, and this is an advantage. Obviously, it's a little bit less spatial, the locality is a little bit less important at that particular point. And once again, what you can see is that this is also reasonable, even if the cluster is large in terms of the deviation from the shortest path. It's about 22% more larger trip, which is nice. This is the time that it takes, and you can see that most of the algorithms here are taking less than 10 seconds to solve. So we can really solve these problems in real time. Some of them here are some of the instances are very difficult, so you can do an approximation there, and you are about 2 to 3% of the optimal at that particular point. So let me show you why this is a difficult problem. And once again, this is like capturing human behavior in an interesting fashion. So this is one of the neighborhoods that we consider. This is inside the city. There are about 500 people there, and they commute less than a mile. And this is how much they can share in the morning. So this is a graph where every commuter is a point, and there is a link between two people if they can share a ride in the morning. So you can see that this is a highly dense graph. This is the same thing in the evening. How many people can share a ride in the evening? You can see that this graph is a little bit less dense, but it's still heavily, it's still very dense. But when you take the intersection between these two graphs, this is what you get. And this is why it's so difficult to get this carpooling system to work. You really need sophisticated optimization. It becomes a very sparse graph when you take the intersection between the two. And that's why you needed the technology that I've shown you before. And this explains to you why some of these systems are not successful, because you have to match. It's not easy to find a match. This is an animation of the system. What you see there is the people, I'm moving it a little bit to, let's say, 8 a.m. You see all the cars coming in and commuting to this parking lot. Blue are the car, and the parking lot are these red dots over there. And you can see that, this is a small city, but you can see that there is still a significant amount of cars which are coming in at that particular point in time. I'm going to show you now the same thing, but for the carpooling system. And what you can see there, what you're going to see is that the cars are starting blue, and then as they pick people, they become pink, and then they become red. And red means that there are 4 people in the car. And what you can see now is that you have a lot of pink and a lot of red, so a lot of car sharing happening, and a lot fewer cars in this particular city at this point. So we really minimize the number of cars tremendously. In this particular case, I told you it's about 2/3. We can eliminate about 2/3 of the car. And once again, you can see that people are picking people, but they're staying in the neighborhood before moving to the city. So it's really exploiting the spatial and the temporal locality. So let me conclude now. I'm closing into the 45 minutes. So what I'm trying to tell you is that we can look at public transit and reinvent it by using novel technology. And this technology basically rely on connectivity between people and the transit system and so on. And they also depend on sophisticated analytics, optimization, machine learning, and so on. So I think we are in a very interesting space where we can invent new mobility services and they can have a fundamental societal impact. They can actually reduce transit time substantially, reduce greenhouse gas emission, and they can also improve accessibility for a variety of people. Behind the scene, I find this area fascinating because we have a lot of science and engineering challenges. Obviously, optimization, data science, and machine learning. We are also spending a lot of research right now in trying to understand people. People are a big component of this particular project. We have to make sure that the systems are going to be used by people, and we're trying to find out, who is willing to use some of these systems? Are they willing to share a car? And when are they moving from taking their cars to a transit system which is on demand? And so we have learned a lot of things about how to design this system through this service and machine learning on this service as well. So this is what we are doing now. We are trying to look at the third case study, which is a very interesting city, Atlanta. Atlanta is the 8th most congested city in the world. And the transit system is very small. It's about 3.4% of the rides, and most people obviously commute alone. The transit time is about 30 minutes by car in average, and about 55 minutes when you take transit. So big difference between them again. So this is a city where we need to deal with these three aspects essentially: the mobility services, the technology, and then the social science. What are people willing to do? And so this is what the project is looking at, but for this particular city. So that's what I wanted to tell you. This would give us a third massive case study compared to the first two ones that we have done. The big thing that we have to do now is make sure that we model congestion in a very sophisticated way, and we basically can deal with different population segments which are very heterogeneous. So these two challenges is what we are focusing on now. So thank you very much for listening, and I'll be very happy to answer any question that, I'll try to answer any question that you may have.